In our last video, we had just begun our discussion of properties of liquids. We will continue it now. Vapor pressure and boiling point also are connected to IMFs, as well as properties of liquids. The vapor pressure is the pressure exerted by the vapor that is found above a liquid at a given temperature. So the pressure here in this container, because there are molecules up there, would be known as the vapor pressure. The higher the temperature of that solution, the higher the vapor pressure. So let's think about this. As I heat water, what starts to happen? Eventually, the molecules start to vaporize into steam. And that requires higher temperatures. So what happens here is that as temperature goes up, so as T goes up, the kinetic energy of the molecules go up. As they are increasing in energy, their movement goes up, and because of that, they are more likely to change from a liquid to a gas. When there's more gas molecules, they're more crowded. They're going to be hitting each other a lot, hitting off the sides of the container a lot, and pressure will go up. Let's discuss boiling point. Boiling point is defined as when the vapor pressure of a liquid equals the atmospheric pressure, the outside pressure surrounding it. Normal boiling point is at 1 atmosphere. And again, we have a connection to IMFs. The stronger the IMF, the higher the boiling point. So the stronger the IMF, the higher the boiling point. The stronger the IMF, the greater the surface tension. And the stronger the IMF, the greater the viscosity. They are all directly related. Let's go through this example problem, and then you'll have a chance to try some as well. So I would like to kind of discuss how I would place these in order of highest to lowest boiling point. So I have to use my knowledge of IMFs to figure this out. So let's discuss the IMFs for each of these substances. Water, you see an H, you see an O. Hopefully automatically you are thinking H bonding. H2S, if I drew it out, looks like this. So it has lone pairs on the center, so it's polar. H2SE is going to look the same. So they're both polar, so both of these would have dipole-dipole forces. Earlier we wrote down that the larger the molecule, the stronger the IMF. And we wrote that under dispersion, but all molecules have dispersion forces. So the larger the molecule, the stronger its IMF. We would only use this if we are comparing two substances that have the same type of IMF. So H bonding is the strongest, so that's going to be the greatest boiling point. And then since both of these have dipole-dipole, we have to look at which one is larger in size. The H2SE is larger in size based on mass, so it would technically be considered the second highest, and then H2S would be the third. So when you do practice problems like this, where you're asked to compare a property, you have to determine the IMF, and then use your knowledge of IMFs to answer the question. Let's do some practice problems now on the next slide. Here, you will be identifying the strongest IMF present. So is it polar? Is it nonpolar? Does it have H bonding because it's unique? If you need to draw the dot structure, please do. And then it asks you to put them in order from weakest to strongest. On the other side, you're just answering questions about surface tension, viscosity, and boiling point. At this time, please pause the video and try these practice problems. Please check your answers. CF4 is nonpolar, so it's dispersion. NH3 is H and N, so it's H bond. Neon is a noble gas, so it's dispersion. And PBr3 is polar, so it has dipole-dipole forces. Put them in order from weakest to strongest, so the dispersions are first. Ne is smaller than CF4, then dipole-dipole, and finally H bonding. On the other side, the greater surface tension is the one with the stronger IMF. So H2O and NH3 have hydrogen bonding, so they're higher or stronger than the CH4 and the Br2. The SiH3Br has dipole-dipole because it's polar, where the SiBr4 would only have dispersion because it's nonpolar. Therefore, dipole-dipole would be stronger. For the viscosity, it would be the same as the three answers we circled above because, again, the greater the viscosity, the greater the IMF. And then for boiling point, it would be the opposite because it's asking for which one is lower. Let's continue our study on liquids and solids. Here we're going to discuss phase changes, which exist between all three states of matter. A phase change can occur when temperature and/or pressure is varied and a change in energy occurs. Most of these you should know. Okay, maybe not the bottom two. When something melts, it goes from a solid to a liquid. When something freezes, it goes from a liquid to a solid. Condensation is gas to liquid. Vaporization is liquid to gas. Sublimation is like dry ice, which is often used in fog machines, so solid directly to gas. And deposition is the opposite of that, so gas directly to solid. Okay. Some additional key terms that are related to phase change include heat of fusion, which is the amount of heat needed to melt 1 gram of a substance. Heat of vaporization, which is the amount of heat needed to vaporize or evaporate 1 gram of a substance. We have some additional terms. Every phase diagram has a critical point and a triple point. The critical point is the temperature and pressure at which one can no longer differentiate between the liquid and the gas state. And the triple point is the temperature and pressure where all three phases, solid, liquid, and gas, exist with each other in equilibrium. We'll see these on the next slide. All substances have phase diagrams that help us to kind of figure out what temperatures and pressures are, this substance in the solid state, the liquid state, and the gas state. Okay. On a test, you might be asked to label one of these similar to the one shown. So the solid state is here, the liquid state is here, and the gas state is here. Okay, so solids are colder, gases are when it's hotter. Okay, solids are when the pressure is higher, gases exist when the pressure is lower. Okay, we're also going to label the triple point. That's the line on the graph where all three interconnect, as well as our critical point, which is where we can no longer officially differentiate between a liquid and a gas. So that's this section up here. A lot of times these are called supercritical fluids because you can't tell the difference between the liquid and the gas state. Okay. So you'll be expected to be able to label those 5 things. In addition, you should be able to answer the questions similar to the ones that I have here. So they want you to identify the phase change. Well, your phase changes exist as you go across the lines on the phase diagram. So if we do this first problem, it says pressure is going to be about 40. Okay, so, somewhere between 5.2 and 73. And then it tells us that our temperature changes from 197 to 230. So if we assume that it starts right about there, okay, and then it's going to end up going to about 230. So it's going from solid to liquid. So it's melting. The next one, we're going to start at a temperature of around 200. And we have a pressure change from 0.5 to 5.2. So we're about right here, give or take. We're going to go up here. So we're crossing the line. We're going from gas to solid, which is deposition. So it's important that you can label these 5 things: solid, liquid, gas, triple point, and critical point, as well as know all of your phase changes. Let's kind of switch gears and discuss solids. Oh, first we have to talk about heat of vaporization and fusion. So we have an equation, Q, heat, equals M times HV. Okay. The HV is the heat of vaporization constant for the substance, and M is the mass. So all you would have to do here to use the equation is say, okay, Q equals the provided mass of 10 grams times water's heat of vaporization, and you would get 22,600. Okay. We do the same thing for heat of fusion. Okay. Mass times the heat of fusion constant for that substance. It says how much energy is required to melt 50 grams of ice. So you would say Q equals 50 times our 334. You would solve that and get right around 16,700. Because it's energy, once again, the unit is joules. Okay. If you would like, you can complete these practice problems. Here are the 2 answers for them, and they would be completed the same way as the problems above. Now, let's talk about types of solids. We have 2 main types of solids. We have an amorphous solid and a crystalline solid. An amorphous solid has no defined shape, and the molecules are not found in any particular position or pattern. And they give you an example over here of cotton candy. And I like that example because, cotton candy is a solid, but it's kind of all over the place. Another good example of an amorphous solid is glass. And if you think about it, if you cracked your windshield, okay, or you broke a test tube, it doesn't break into the same exact pieces every single time. Okay? That's because glass is amorphous. Crystalline solids we'll cover in more detail are when you have molecules or ions that are arranged in a regular symmetrical structure. Okay? So really, pretty much everything else fits here. So things that are ionic, covalent, okay, so on and so forth. So I just put everything else. The next slide has a chart that we're going to complete on the 4 major types of solid. Here you will see the chart completed. Ionic solids are nonmetals and metals. Okay, and they have electrostatic attractions between them and relatively high melting points. Molecular solids are nonmetals only and have lower melting points, held together by IMFs. Network solids are really unique, pretty much just diamond and graphite, very hard and have very high melting points. And finally, metallic solids are metals, and they can conduct. This concludes our study.